My name is Mite Mitreski. I work for a Swedish company called Klarna. Previously, I worked for some consultancies in Macedonia, where I was also involved in the JUG. At the moment, I'm also part in some other communities, like expert groups in the JCP, VJUG, and so on. Today, I wanted to share with you some experiences that I had in the past couple of years running and developing systems where microservice and service-oriented architectures were used and in a distributed manner. Okay, so enough about me. Yeah, you've probably seen something like this. The idea is, with microservices, it's quite simple, actually. So instead of having one application, we can split that application to 4 separate applications, which are grouped by functionalities. So they are separate physically applications running through the whole separate stack. So the database is different, actually the technology can be different, and so on. So the idea is really simple. But on the other side, like from microservices, we call the monolith. And I mean, monolith, it cannot be good, right? I mean, it's really bad, right? It sounds bad, right? But then, like, we get to a point like saying if this like monolith is bad, and we need to split this application, then really how big this application should be, like 1 method, like 2 methods? Should it be like 1 team? You can find a lot of buzz around the internet about this. Everyone is actually fighting about whether or not the right amount of this should be, what the right amount of this should be. I like the definition that comes mostly from the Amazon side. At least it's attributed to Amazon. It's called the two-pizza rule. Basically, the team, you should be able to, from running microservice, you should be able to feed him with 2 pizzas. So if it's too big, you cannot really feed them. Then you have some people who eat more. Then, again, I guess you cannot feed them. But yeah, it's like a rough estimate. It needs a good estimate. Actually, it has proven throughout various studies, actually, that teams who are bigger than these kind of sizes cannot actually develop a good product individually. And it's actually even true for companies. There are studies for companies that have like that are larger than 300. Some companies intentionally split the company and relocate the persons, because after 350 persons, you don't actually know each other. So you cannot communicate between the teams. But that's like a separate issue. So to get back into the microservices thing, like 2-pizza rule is good enough, I guess. So the monolithic architecture, we said it's evil, right? Everyone says it's evil, so it's gotta be evil. It's really funny, actually. A lot of people start using the term now for anything that they don't like. They call it, this is a monolith, it's really bad. Well, I mean, we've been writing applications in various different ways for a long time. So this doesn't mean that actually the monolithic applications are bad. Everything has its own purpose. What I actually like from microservices is that they have been with us for quite some time. They are not really such a new concept, even though it got popularized mostly by the ThoughtWorks folks. For me, actually, I like the fact that microservices are kind of the Unix way. So, I mean, you develop one application that does one functionality, one thing, and it does that thing really, really well. If you take a look at the old commands that we are using nowadays, actually, if you take like copy or cat or like ls, those commands are written in the 70s. Oops, sorry. This is bad. Maybe I shouldn't be using this as well. Sorry. Yep. This is not good. Okay, sorry. Okay, so those commands actually from the Unix systems are actually written in the 70s, and we are still using them today, right? I mean, they still work. And if you take a look at their source codes, they haven't really changed all that much from the 70s. And we still use them nowadays. And that's the whole idea of this, that actually the business side gets the value at the end. That you have an application that you can interact with it. And that application works for long periods of time. And also it's replaceable. There is also the replaceability aspect of it, that the application can be replaced at any point of time without making too much effort or big constraint on the business side. Actually, there is this Amazon so away. Everyone, a lot of people actually attribute the success of Amazon from the 2000 to Jeff Bezos' decision, which was basically he forced every team to have an API. So each team has an API. It doesn't matter how the API. It can be SOAP, it can be RPC, but it's an API. So each team communicates with other teams through an API. They will not communicate by doing shortcuts, by reading stuff from their database, by making some other customizations. They will interact with the applications via an API. And if you look at the Amazon applications, some of them have bad interface, but they have an interface. Everything has an interface. You can interact with anything that they have built that's publicly available, even stuff that are built from the 2000s. And it's something that I really like, and I believe that it is the right way to go forward. So they kind of split this application, and now really we allowed a lot of teams to use their favorite toolkit, their favorite coding language. Maybe we didn't allow that, but for sake of the argument, let's say that we did. Then what do we really need to standardize? If we are not standardizing the containers themselves, the whole microservices, we are not standardizing them. The teams can do whatever they want in their application. Then we need to standardize the interface between them. So we need to make sure there aren't any issues when this whole application evolves. That's actually the topic I want to concentrate mostly on, is how to avoid coupling these microservices. You know what's worse than a monolith? A distributed application that acts like a monolith, that's tightly coupled. And you can find examples of this everywhere, actually. And it's really quite easy to do. And I'll show some examples of how noticeable this coupling is in certain areas. But in certain areas, it's really hidden. And we'll see some patterns, actually, on how to get away from coupling these applications. I have worked on a project that was initially started well, and then sort of evolved into something like this. And it's really difficult to get back on the right track on a distributed application that's a distributed monolith, really. Even though it's like separate applications and so on. They have so much dependencies, it's really difficult to maintain. So one of the most basic ways to actually create coupling is the URL coupling. So you have one service. He needs to know the URLs of all the other services. So let's say the other service needs to change the URL for whatever reason. So every client must also update the URL. So technically, they are not independent. You cannot release them individually. So you don't have microservices in that case, because they are really coupled. You cannot release a service A because service A depends on service B to having this specific URL. In some applications, you cannot really avoid at least part of this. But one possible way to avoid this is something called the link service pattern. So basically, the client, which can be a server actually, but let's say we're going to call it a client. Let's say it calls the first server. And after some period of time, he needs to call the second server. What you can do, actually, is to decouple these two machines. It's really simple, actually. The first server, in the response, will contain the location of the second server. So this is something called link service. basically what you do is in the response from the very first request, you have the URL of the next machine. So basically you remove the dependency of the second server between the between the client. This can be actually even extended a lot more. This is actually Hypermedia as an engine of application state, or HateOS, or there are actually tons of pronunciation of the same word. Let's look at a simple example. Basically, we have like a customer. This would be like the JSON serialization of that customer. The Hypermedia way would be add a link to this customer. So at the moment, this kind of links to its own machine. But technically, if the client actually is following this reference, he's following maybe another server. And the client actually doesn't need to know where this location is. He can get this information from the really first request. And this actually allows this decoupling of the URLs to some extent. Actually, there is this something called Richardson maturity model. Martin Fowler has this, and there are like tons of articles in the same topic, actually. Basically, how do we classify our APIs? So the basic most level of this like coupling on this end is like this swamp, where we have like procedure calls, we have RPC, we have really tight coupling. After a certain point of time, we realized that that's really too hard to maintain. We got to a state where we have resources. We have JSON, I don't know, maybe XML or whatever. It doesn't really matter on that serialization technology. But we have like the concept of resource. We have the concept of customer and so on. Then the next level would be to properly use HTTP verbs, which means on errors, we don't return 200, right? Once we get to that kind of state, next state would be this: get the links. Get the links to the services. This is why we need the links. It's not really because it's that much easier to navigate through the thing. Even though it is easier, but like, this is the main reason why we actually need the links. And then we have the awesome glory of REST. One other simplification that you can do is something called a service connector, where basically you provide a library. So this is kind of controversial in some microservice groups. Basically, you give the client a client library, which is like acts like a connector to your service. So the client doesn't know this. You kind of extract the communication. You give him a simple API that he can work with. But he is, to some extent, coupled with that library. And unless you find some way to actually update the client libraries all the time, then you kind of still have the URL coupling. But to some extent, you kind of simplify the client, and you extract this URL coupling from the client side. And this is actually the most controversial of all, is to have a registry. It's most controversial because a lot of technology is dependent on something like this. So what's the concept of having a service registry? You have a service registry, where all your service providers register to, and then the client actually asks the registry, where is my service, before making the request. And then he gets where his service is, and he does the call. Very simple, right? Nothing too fancy there. But what happens actually, all your microservices now are tied and coupled to this registry. So if this registry goes down, what do? There isn't much you can do, actually, except make sure this registry doesn't fail. So how do you make sure this registry doesn't fail? I mean, there are various solutions on doing this. Most common actually is Apache Zookeeper, where you actually can actually make sure that the reliability of the system is so high that the failing of the registry is not an issue anymore. But this can, in theory, still happen, even though you have, like, I don't know, 20 redundancy of the services and so on. So that's actually the whole controversy of this, because even though you kind of decoupled every microservice, you have a registry. you kind of depend on that registry being there. Some people actually use a simpler solution like DNS for this. There are some issues with the DNS and the delays of DNS actually, and how do you actually maintain that? There are good articles from the Spotify team, I think, about how they are doing this with DNS. So the issues are mostly when some of the servers, actually the service providers that are in this registry have failed. How do you update the registry? That's like that's something that you need to actually worry about, because it's not really an instant depending on the implementation. Okay, so this was the URL-based coupling. We also have actually a temporal coupling. So you have one service A, you have a service B. When service A does request to service B, it expects the response to be processed in X amount of time. When you think about it, for most of the business applications, this is not really a requirement. You can actually get away with this. But this is actually mostly like synchronous calls being made between the services, and you expect the processing to finish. But this is, in high-load scenarios, this is not option actually in many cases. So let's see actually how can we avoid this. I mean, okay, one simple, obvious choice is like, let's go async, right? The client makes a synchronous request. He gets that this thing has ended. And then what happens? So there are two options that you can go with it after the request has been sent successfully. We have acknowledgement that the request has been successfully received, but we don't know whether or not the processing has finished. So this line here, actually, there are two ways you can go about this. You can have the callback way, where the server does a callback towards the client. And you can have the pulling way, where the client pulls every X second. You need actually both ways in different scenarios. Everyone would say, like, yeah, let's go with the callback way. But what happens if you have a high load on the client, and the client actually cannot process that many callbacks? The pulling way is the only option to go then. You can pull on a certain rate that you know that the client can process. So that was, if you have like high load, you want to avoid high load on the client. But really, what happens if you want to avoid high load on the processor, actually, the actual processor itself? So when the client actually does this request now, it does it asynchronously again. And he gets acknowledgement from the queue that this is ready to be processed. Kind of similar. The request processor then can actually read from the queue on his own pace. So he can actually decide how much he can process. The client still needs to actually get a response from this to know how it was processed. So again, it can be a callback. It can be a pulling way. There are those two options. What this enables is actually high-load processing. And the queue can be anything, like RabbitMQ. Kafka is really popular nowadays for this. But this allows you to have a high load that the processor can handle. And it avoids the synchronous need for the synchronous processing. But there is also the data structure and the functional coupling of the application. Let's say you need to represent percentage in your application. Anyone has an idea what he would use as a data for representing percentage? Yeah, don't be shy. Would you use like an integer, like a double, like? Okay, let's say we go with an integer approach. And we have like, what would be the base? So 100 would mean 100%, and 1 would mean 1%, right? Actually, some teams have actually done this in the public APIs, and then actually needed more, actually. They needed to go under 1%. Actually, I think that Google Cloud had this issue. But actually, a lot of other things are really not straightforward. Let's say the numbers, for example. How would you represent a number? Like phone number. So for number, you can say, like, I can use the local format. I can use, like, there is, like, I37 or something like international format. There is, like, another international format where things are formatted. Just because you have a specific format, actually, you make assumption that the client will be using that format, and actually all the other services will be using that format. So you cannot actually get away from that. Like, if you're using the national format, then you actually must provide also a country code. And the country code is something that it's also a standard. You can use some ISO for represent the country code, but there are some countries that are not there. But regardless of that functionality, let's say that you have picked a specific format. You have actually coupled everyone to use that format. Everyone must now use that format. And there is no way to escape from that. So these type of things are really difficult to get away from. But it's something that you need to think up front when you even start with developing of these systems. As the application grows, we add stuff actually to every services. So we need to actually define what's a non-breaking change for us. I mean, you can go always say that I'm going to break all the other systems, but that's not really an option. For REST, actually, for REST, let's say, RESTful-based systems, we can say that the addition of any type of field, of like cookies, adding like response body where there wasn't any response body, adding stuff, basically, should not damage the client. Some clients actually develop them, they do like strict schema validation. This does not work in microservice architectures. You cannot do that. If you do that, you're coupling, again, the two systems. Like if one day you were returning 200 and now you're returning HTTP 201, that should not break the system, in most cases. That should really not break the integration in any way. If you change the order of fields, again, it should not break the system, even though it's like XML or something like that, regardless of the serialization format, actually. This should not kill the client. The integration should still work. Adding stuff that are part of some set of values should also not hurt. So even though this like looks straightforward, actually in practice, you can see this all over the place, that things break just by having this. There are actually the Android library that's most popular for sending like HTTP client. I think it was OK header or something like that. OK HTTP. It breaks actually if you add a response on for that like 201, yeah, on a post request. If you add a response, it breaks. And up to like 2 weeks ago, it was still breaking like that. I mean, there is an issue file on that, like of course, but I mean, if HTTP, the protocol allows it, you should also allow it. I mean, you shouldn't rely on some assumptions like that. Which kind of gets me to the point of versioning. So I'm not talking here about semantic versioning where you do like, I don't know, no breaking changes. When you do a breaking change, you kind of change the version and so on. I'm talking about the APIs of the microservices. So how do you version the APIs? So some companies do like change in the URL. So they add v1, v2, v3, and so on. And I guess this is OK for companies like Twitter and so on, where the clients are usually some startups that are quite agile in changing to the new API. But if you have like a system that you have like slow changing customers and slow changing consumers of your data, you cannot really just change the URL and everyone would start working all of a sudden. This will not happen actually. Some other people like add some custom headers. So they say like, okay, use now from this header API version 2 or like X API version 2. But actually there is no need for adding custom header, even though this like solution is somewhat better because the URL kind of stayed the same. You can actually use just content negotiation. And actually it's really supported in almost any framework, like Spring supports this, JAX-RS supports this, like tons of other frameworks supports this. Instead of adding custom headers or like doing changes in the URL, you can just use the accept header. And the clients that want to use the version 2 of the API will use this VND microoperation v2. And they will get the second version of the API. But the old clients will still be able to use the same URL, and it would be seamless, the change for them. So if you actually have like a client library, when they update, both of the versions will be running on the same machines, on the same service, and so on. Of course, this doesn't allow much changes in the URL, but that's like another problem. Which brings me to the topic of stability. So previously you had like one application, right? Now you have like 16 applications. They're distributed. It's a network. It's gonna fail. It's gonna fail, no matter what you do. Like put them in the same centers, put them in the same regions on the AWS. Do whatever you want, like massive optimizations on Linux level or on every possible level. It's gonna break at a certain point of time. Some requests will not get there. So there is this great book called Illicit. It has nothing to do really with releases. It's like an unfortunate name. But it's mostly about stability patterns in your system. I'm going to talk for some of them and give like a brief overview of those. But yeah, a lot of frameworks actually have this built in. Some of the concepts are really quite straightforward. Like timeouts. You know. Everyone uses timeouts, more or less. So you just set a timeout, and you expect this to be finished unless this is processed in X amount of seconds. Yeah, really straightforward approach. And this allows your system to actually break on a faulty server request. But what happens after this? Like you're getting a lot of timeouts from some external service. So there is the concept of circuit breakers. So circuit breakers in electricity, when you have like overcharge, the fuse goes off, and it doesn't destroy the system. It's just this part of the electricity network goes down. It's the same approach actually in the microservices. You basically stop only a portion of your system. You can go with some fallbacks on that system. So what we do actually for almost all external service where we can have a fallback, we have some kind of fallback when the system goes down. We can still process and work and function 100%. Well, 100% more or less. Certain functionalities sometimes are not available. That's not really what the business side of things should look like in real life. But with less functionality, you can still have a running system that has like high reliability. So, yeah, it's like a fallback approach. Basically, you're sending to the server, the server on the top. This is like your primary machine. Once the fuse goes off, you start sending to the other machine. It's a really simple concept. You just do a fallback. Like on most of the cloud providers, they have some data storage, and you can use that to queue up the data and resend that. I mean, there are a lot of ways you can go about this. You can queue up things in memory. Some frameworks actually have this by default, like there is like the concept of redo lock and so on. But it's really a simple approach. You just need to handle the case where this service goes down. So also you need to kind of define what this service going down means. Some microservice architectures kind of use health checks, so they all ping around to see if the service is up and running. That may or may not be reliable in your scenario, but one approach on the client side is that when the X amount of threads are all busy for X amount of time, you kind of blow the fuse. And that's actually kind of mostly the default implementation of most pools, like connection pools, thread pools, and so on. One other simple concept is the bulkhead scope concept. So you have a ship. In the ship, you have like these separate sections and groups. So you don't want the ship to float if one of these breaks. What you do is you separate them in such way that even if there is water leakage in some of them, the ship doesn't go down. It's the same thing what submarines do, like most of the ships actually have that. That's why you have that spinning thing on the doors. So you can actually apply the same thing in the software. You can apply the same thing in the microservice architectures. One really like the first straightforward scenario for this kind of pattern implementation is the connection pools. So let's say you have like 2 servers and they share the connection pool. What happens if the first server misbehaves? Just because the first server is misbehaving, we cannot send requests to the second server. This first server is setting up all the resources from the same connection pool. The simple really approach is like have 2 connection pools. You kind of split. You have created a bulkhead for the machine. So now you have 2 separate connection pools. And this is like the most straightforward approach. You can actually do this throughout your applications in many different ways. And you should be always thinking about this. You should be designing for failure. There is also the concept of Handshake, which is, at first it sounds really strange because like Handshake, it's mostly like network, right? But the idea is really simple also here. The client requests the server, how much can you process? And the server says like I can process 10,000. And it sends like 10,000 requests to the server. This allows us to have a stable way of controlling the flow of the data. It adds an additional overhead, but it kind of helps the stability of the whole system. So the client sends a request, how much I can process, the server says 10,000, that's okay. The client can send this 10,000 there. So this was like more about the stability of the system. So we can also have like simplification of the APIs. If we have like some related service calls, the client doesn't really always have to know about all of these services. What you can do actually is group certain services into a like API gateway. So the API gateway is the thing that actually does the calling toward the other services. So this actually reduces usually the load of the network from the client side, and actually additionally simplifies the whole logic. So if you have like multiple services that you can have a grouping of, you actually put up an API gateway in front of them. You don't actually merge them, but you put up an API gateway that allows you access to those services. One other thing that kind of helps the tracking of the system is the use of these tracking IDs. They're also called correlation IDs. Actually, they have like tons of names. It's a simple idea. On each request, you put up an ID on the first service. So that ID is propagated to the second service, to the third service, and so on. Now you can actually grab the logs or grab the whole application data or so on, and see which request caused what changes throughout the system. Because now previously you had one application, it was really simple, right? Everything was there. But now you have like 5 applications, 10 applications. You need to see how this request affected all of these. This kind of solves the trackability of request kind of issue. But if you need really more deeper traces, so let's say this closure application is calling 10 other applications with just one request. So when the first request reaches closure, it needs to call 10 requests to other applications. How do I know that this thing created all those 10 requests? Maybe sometimes there should be 8, maybe there should be 9. We still haven't run into the need for that deep level tracing on any of the systems, but a lot of other systems have actually run into this issue. So there is this Zipkin project. It's Twitter-based project. They allow tracing on different distributed systems. So using this, you can actually trace throughout your services how this request was processed. For us at the moment, the logs are good enough. But yeah, I mean, we are still looking into this, and probably we're going to end up using something like this. If not Zipkin, there are several other ones. Actually, this Zipkin is based on like a paper from Google Draper project, I think it was called. But yeah, that's the basic idea, how to track from one request what's happening throughout the system. And of course, it's a distributed system, so you kind of have to make some trade-offs. Like all the database providers, mostly from the NoSQL side, they say like, yeah, we have this, we have like this much performance and this, and they usually like leave out the other side of things. So CAP theorem applies in the distributed system. So you either have like high consistency or high availability. You have two of these. You cannot have the three of these. You cannot have like huge load with tons of partitions and have availability and have consistent data. You have either Cassandra type of application where you have like availability and partition tolerance, but you don't have the consistency. It's eventual consistency. Now, there is more fine-grained trade-offs in certain applications, but you still will need to do some kind of trade-off like this. You're always giving up something for something. It's not a silver bullet. And of course, I mean, you must automate everything. Like, yeah, I'm gonna pull this off. So, I mean, you need to have everything automated. You cannot have any manual task. Previously, it was one application. Maybe it was okay to have some part of the process to be manual. Everything must be automated. You must use like some kind of solution, either like Docker or Vagrant or I mean, there are thousands of these. We at the moment use a combination of Docker, AWS, Jenkins. Yeah, this is actually some colleagues of mine masked there. That's Jenkins. And I mean, you also need a good monitoring. You need to have the logs in a central location. So Splunk or Kibana are usually the solutions of choice, but there are thousands of these. There is Logi and so on. So you need to have the logs on one more central location. So most of these ideas actually come from this book called Service Design Patterns. It's forwarded by Microservice Fowler, so that I guess makes it really good. It's more applicable to microservices now than it was ever applicable to the SOA designs. And of course, I mean, you must still have like extremely good continuous delivery. It's even more important now. You have more applications. You still must keep the old principles that were there applicable to the one monolithic application. This doesn't really solve that kind of issue. The microservices solve some problems, but then they create others. So, are microservices the future? Yeah, I mean, I don't know. I don't think anyone knows, actually. If you have a look, it's really the buzzword. I think in this conference, there were like how many? Every other talk was microservice related. They've been here in the past, that's for sure. Some aspects of it were in the past. Some say like OSGI is microservice. That may or may not be true. But in the concept, actually, it's mostly about the organization of the company rather than the technology. Because the technology has been here, actually. It's nothing new, actually. We've been using it since Unix days. So it's more or less the same. Although I cannot answer this question, if you have a look at the trends, and I always tend to update when I give some talk, so this is quite recent. You see, all of a sudden, like a year ago, this is like from Google Trends, and this is from, indeed, the job site. So this is like what you call a bias, actually. So all of a sudden, something appears, and it skyrockets. Yeah, tons of companies are using it. It really helps in a lot of different ways. I'm still saying that it doesn't make sense for every application. It actually doesn't make sense for a lot of applications. The book, actually, and the article are the Multifollow article from Microservices and Building Microservices from O'Reilly. I would suggest you to at least read the article. It's quite extensive, and it provides most of the details that you actually really need if you want to go in this road. And thank you, and I'm open for questions. Yes? Yeah, the idea is like the client broadcasts that he is now into the system. There is that approach also, yes, but there are also downsides to that, right? That's not really, it's not really, again, a silver bullet, right? I mean, what happens if some of the clients are misbehaving and misbroadcasting something that they shouldn't be misbroadcasting, right? It depends, it's kind of the answer always, but it kind of depends on the system. It really does depend on the system. What do you expect to gain from that? Yeah, I mean, we need service registry in some areas. We are using Zookeeper for like really like the queuing stuff, but everywhere else we try to avoid all of this as much as possible, because this is like really easy to get into huge problems that you cannot really trace well afterwards. Like it's extremely hard. Any other questions? Okay, I'll be around at least for the party. So yeah, thank you.